Oh,
Yes,
yeah, already
streaming
done.
done. Streaming also done.
Okay, thank you. So, shall we
Thank you, sir.
start
Now we can start.
Okay, great. Thank you. Thank you.
Great.
Yeah, good afternoon all, and welcome, Professor Yasunari. Yeah. Yes. And to all, everybody, Dr. Krishnan.
Namaskar.
Thank you. Nice to see you.
Dr. Trust, yes. So we can start, right?
Good afternoon, all. National Science Day is celebrated in the honor of Sir C. Raman, who discovered the Raman effect on 28th February every year. Today, on this special day, I'll welcome you all on behalf of South Asian Meteorological Association SAMA, Vidyarthi Vigyan Manthan, Government of India, Vigyan Prasad, Government of India, and SRM University, Andhra Pradesh, to the webinar on the life and work of two renowned Nobel laureates, Professor Sukuro Manabe, meteorologist, and Professor Klaus Hasselman, oceanographer. Professor Manabe, Professor Hasselman, and Professor Giorgio Parisi received Nobel Prize in Physics in 2021. I now request Dr. Madan Lal Shrestha, academician, Nepal Academy of Sciences, to present the welcome address.
Yeah, thank you very much. First of all, I would like to welcome you all. So, Mr. Chairperson, the distinguished speakers of today's webinar, Professor Tetsuzo Yasunari and Professor Krishna Pachutarao, a distinguished guest and participants. Namaskar and good afternoon. So we welcome you all to this webinar organized jointly by SAMA, Vigyan Prasar, Government of India, Vidyarthi Vigyan Manthan, Government of India, and SRM University, Andhra Pradesh. South Asian Meteorological Association, in short, SAMA, has been working towards the upliftment of the meteorological science in South Asia and taking it beyond by conducting various activities. Today's webinar is one of them, with great importance to highlight the 2001 Nobel laureates, Professor Shikuro Manabe and Professor Klaus Hasselman, for their invaluable contribution in the field of meteorology and climate change science. I had the opportunity to meet and interact with Professor Manabe-san during my stay in Nagoya University in the year 2009 to 10. Professor Manabe is a down-to-earth human being, encouraging always the people around him. Climate scientist Shukiro Manabe and Klaus Hasselman were recognized for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. It would be appropriate to recall the earlier Nobel Prizes given in the field of atmospheric sciences and climate change. I think if you remember, in 2007, Nobel Prize was awarded to Vice President Al Gore and IPCC, which recognizes the importance of human-induced climate change and action needed to understand it and mitigate it. And likewise, in 1995, we remember the Nobel Prize in Chemistry given to Professor Roland Molina and Krishnan for their work on the global environmental problem arising from ozone depletion by manufactured chemicals, and some of which are the major greenhouse gases. This time, in 2021, Nobel Prize in Physics, there is a distilled scientific basis of climate predictability, detection of change due to known external forcing. Professor Manabe focused on simple models incorporating the well understood fundamental physics of radiative transfers, atmospheric dynamics, and land and ocean processes. Whereas Professor Hasselman, on the other hand, dealt in separating the fingerprint of forced climate change. Mostly it is the anthropogenic from the noisy, unforced variability that is inherent in the climate system. His outstanding signal-to-noise studies in climate system help to unequivocally conclude the human influence on climate. I think it will be unfair in my part not to mention another Nobel laureate of 2021 Nobel Prize in Physics, Professor Joseph Parisi, who discovered hidden patterns in disordered complex materials. I'm sure that his contribution extends also to many fields as well as in the field of climate science. So today we have two eminent scientists with us as the speaker, Professor Tetsuzo Yasunari, advisor, KCCAC Japan. I'm very happy to mention that my association with Professor Yasunari goes back to early 70s at the time of the glaciological expedition to Nepal, a joint Japan-Nepal venture to explore the Nepal Himalayas. And another eminent speaker is Professor Krishnan Rao, head of the CAS IIT Delhi, India. So these two speakers, I think, will shed light on Professor Manabe and Professor Hasselman's work, respectively. We sincerely thank them for accepting to give their talk in this seminar. In addition, we have many distinguished personalities taking part in this webinar, and I'm sure that we all will be benefited from their deliberations. At the same time, I request you all to actively participate in the webinar, including the discussion sections. With this, I welcome you all once again and wish for a successful webinar on Nobel laureates' works. We appreciate for your gracious presence. Thank you. Thank you.
Thank you, Dr. Shrestha. Now I invite AVM Professor Dr. Ajit Tyagi, Chairman SAMA, to give his remarks.
Thank you, Dr. Shrestha, for your welcome address, highlighting the work of two eminent speakers and welcoming. And I join you in extending warm welcome to our distinguished speakers, Professor Yasunari and Professor Krishnan Rao, and other distinguished participants. I'm also thankful to Dr. Krishnan, who, despite his busy schedule, has agreed to provide a concluding remarks. South Asian Meteorological Association, along with its 9 member countries of South Asia, has been actively engaged in the promotion of science of meteorology and its application for societal goods. In the series of these activities, along with our partners, I am thankful to Vigyan Prasar, Vidyarthi Manthan, and SRM University, Amravati, for organizing this climate science quiz to promote climate awareness among the students. This is a 1-month-long online quiz which will be culminating on 23rd March, World Meteorological Day. Along with this, today's webinar is been highlighted. It's an important event for SAMA and South Asian countries, the young scientists especially. The idea is to inspire young scientists in the field of meteorological research, and especially on the climate modeling and its latest developments in these areas. So we also are thankful to our all supporting members, advisory council members, and expert team who have been actively working along with Vigyan Prasar, SRM University, to organize the online quiz and also today's webinar. I wish webinar great success. Thank you. Jai Hind.
Thank you, Professor Tyagi. I now invite Professor D. Narayan Rao, Pro Vice Chancellor, SRM University, Andhra Pradesh, to give his remarks. Sir, you are muted.
Yeah. Our beloved Vice Chancellor, Professor V.S. Rao Garu, the Dean, Professor V.V. Babu, Professor Ajit Tyagi, Chairman of South Asian Meteorological Association, SAMA. Dr. Someshwar Das, Convener of SAMA. Dr. Madan Lal Srestha of Nepal Academy of Sciences, the well-known atmospheric scientist of global repute, and today's distinguished speaker, Yasunari Sensei, Head of the Department of Atmospheric Sciences, IIT Delhi, and today's distinguished speaker, Professor Krishna Chudrao, Dr. Krishnan, Director of Indian Institute of Tropical Meteorology, IITM, Pune, the moderators, Dr. Swagata Priya and Dr. Mohan Kumar Das, Dr. Fatima Akhtar of University of Dhaka, honorable members of the Executive Council and members of SAMA, deans and directors, heads of departments, faculty members, research scholars, other colleagues, and bright and young students of SRM University, school children and teachers of different schools, my colleagues, Professor Ajit Thapa, Dr. Lakshmi Kumar, Dr. Murali, all the participants of the National Science Day, my dear members of print and electronic media, ladies and gentlemen, I am very glad to associate myself with the National Science Day celebrations being organized by SAMA and SRM University jointly. Many of the young students present here are aware that the incoming short wavelength radiation from the sun is absorbed by the earth and re-emitted towards as long wavelength radiation, OLR. The atmosphere absorbs a part of the outgoing radiation and warms up, which is known as greenhouse gas effect. This warming of the atmosphere and the ground below the atmosphere is affected by the greenhouse gases, water vapor, carbon dioxide, methane, and other such gases. Due to numerous development programs and also due to significant increase in human activities, fast and adverse climate changes are taking place all over the world. The climate change has now become a common enemy to the world and posing problems of different types to the entire humanity at large. As the Earth's temperature is increasing, glaciers are getting melted, and the mean sea levels are increasing in an unprecedented rate. It's forecast that the increase in the mean sea levels will severely affect several cities, including Paradeep, Visakhapatnam, Chennai, Tuticorin, Cochin, Mangalore, Bhavnagar, Kandla, Goamargam, and Mumbai, affecting several crores of people living in these regions. For the youngsters, if the house in which you are living is not good, you will move to another house in the same street. If that street is not comfortable, you will move to another street in the same city. If that city is not good, you will move to another city. And then, even if that city is not good, you will move to another country in the continent, or you may go out of the continent. But if the entire world is not comfortable to you, where you will go? So there is a bound and responsibility on all of us to protect the planet Earth. Thus, to create awareness, particularly amongst the young students and others, I have requested our long-term friends, Dr. Ajit Tyagi and Dr. Someshwar Das, to organize lectures of the Nobel Prize winning works of the Nobel Laureates, Professor Sukuro Manabe and Professor Klaus Hasselman. They have kindly agreed, and on behalf of SRM University, through this forum, we express our gratitude to South Asian Meteorological Association for their kind gesture. For information of many of the members present here, I wish to inform you that SRM University Andhra Pradesh is established in July 2017 as a multi-stream research intensive university. Presently, we are offering BTech and MTech programs in different disciplines, and we have about 5,600 students from different parts of the country and a few students being foreign nationals. About 180 students, including a few net qualified, have enrolled for PhD programs in different disciplines. We have appointed 200 faculty members having PhD degrees from premier institutes such as IITs, IIS, and reputed foreign universities. 4 DST Inspire faculty, 1 DBT Ramanujan Fellow, and 1 Srinivas Ramanujan Fellow are working at SRVP as faculty members. In the year 2018, we have started School of Liberal Arts and Social Sciences and also School of Entrepreneurship and Management to provide holistic education as envisaged by National Education Policy 2020. Our faculty members are quite active in research and have published more than 700 papers during the last 2 years in highly reputed journals, including Nature, Nature Communications, Nature Microbiology, Proceedings of National Academy of Sciences, PNAS, IEEE Transactions, and other reputed journals. Some of our faculty members have published 20 papers in Nature Index journals. Dr. Karthik Rajendra and Dr. Imran Pancha and Dr. Lakhvir Singh are recognized among the top 2% scientists of the world as compiled by Stanford University. Many of our faculty members have received sponsored research projects from DST, DBT, National Supercomputing Mission, DRDO, BRNS, QGC, DA, and a few industries. One faculty member, Dr. Sudarshan Govindarajan, received the prestigious DBT Welcome Trust Award. We have established SRM Amar Raja Center for Energy Storage Devices jointly with Amar Raja Batteries Limited, the leading battery manufacturer in the country. IMD has established its Center for Weather Forecast in SR University campus, and from this center, weather forecast is being provided to the entire state of Andhra Pradesh. We have also started a few special projects, namely development of gold foam for jewelry applications in collaboration with Tanishq Jewelers of Titan Industries, Hari Vaman Petya of Maharashtra. 3D printing of gold jewelry, a unique and pioneering initiative, once again in association with Tanishq Jewelry. We have initiated 3D printing of bioimplants in association with Concordia University, Canada, and All India Institute of Medical Sciences, AIMS, Mangalagiri. Metal active manufacturing for strategic applications in collaboration with IIT Hyderabad, IIT Jodhpur, and RCA Hyderabad. At SRM University, we provide the students research-based learning for knowledge creation and innovative ideas. Further, we train the students with a desire to do and with a desire to learn and enable them to take up challenging tasks that they may encounter in their careers in the next 3 to 4 decades. After all, the BTech student is only 21 years. He will be having an illustrious career for the next 4 decades. We train them in such a way that he or she can encounter challenging tasks in their careers. We do well realize that universities are viewed as creators of new knowledge, innovative ideas, providers of talented and skilled manpower, agents for social changes, symbols of international attention and prestige. With that realization, we have established New Age University, SR University, Andhra Pradesh. Jai Hind, Jai Bharat, and Jai Vigyan. Thank you one and all.
Thank you, Professor D. Narayan Rao. Now I request Professor Dr. Someshwar Das, convener, Sama, to give brief description of activities of Sama.
Thank you very much, Dr. Rohini. Let me share the screen. Just a few minutes. Just trying to share my screen. Host disabled participant screen sharing. Yeah, I am disabled, I see. Can I be enabled for sharing my screen?
You can start, sir.
Okay, yeah. Is my screen visible?
Yes, it's coming. Yes, coming.
Okay,
Yeah,
good.
visible.
Just 1 minute. Yep. So thank you very much all. Well, this South Asian Meteorological Association, SAMA, was established on 3rd of August 2020. I'm going to give you a brief of the activity that we have conducted since its establishment. First of all, who we are. The South Asian Meteorological Association is a non-profit scientific society of 9 South Asian countries, including Afghanistan, Bangladesh, Bhutan, India, Maldives, Myanmar, Nepal, Pakistan, and Sri Lanka, engaged in promoting regional cooperation in the field of meteorology and allied sciences. Our vision is sharing knowledge of weather and climate without borders. And the mission is meteorology for the sustainable development of the region. Our objectives are foster interaction amongst professionals working in meteorology and allied fields in South Asia, advancement of meteorological and allied sciences in South Asia, application of meteorology and allied sciences for the sustainable development of the region, communicate knowledge of climate change and extreme weather events to the public through citizen science and outreach programs, and promote public, private, and academia partnership for the promotion of the meteorology and its societal applications. Well, we have a dedicated team called Executive Support Team of SAMA, who have made so many things to happen in the last 1.5 years. We made the constitution of SAMA because it is a forming organization. We developed the website of SAMA. We started publishing the annual newsletter of SAMA. We are trying to bring many like-minded organizations to one platform. We have started a monthly webinar series. We have got more than 319 members, including life members and student members. The SAMA is guided by advisory committee and driven by executive support team. Well, there are many activities. I will only quickly display the activities carried out since 2021 and 2022. In 2021, we celebrated the WMO Day on 23rd of March, in which we invited eminent speakers and eminent scientists to talk on oceanography, ocean and atmospheric sciences. And we conducted a webinar on lightning resilient in South Asia. On 22nd of April, we conducted a webinar on the heat waves in collaboration with IRADE, Indian Meteorological Society, and SAHIN. That was on 6th of June, 2021. Then we conducted a webinar on the restoration of Himalayan ecosystems. That was on 17th of July. Another celebration we did was the Foundation Day celebration of SAMA. That was on 3rd of August. We conducted webinar on the Asian Precipitation Experiment, AsiaPax, on 4th of September 2021. Our Professor Toru Terao from Kagawa University, who is leading this project, AsiaPax, was the speaker for that webinar. Then we had the first meeting of the scientific committees on 16th of January. SAMA has constituted different scientific committees, namely education and outreach, numerical weather prediction, satellite meteorology, radar meteorology, air pollution, and climate change. So we're trying to increase the capacity in all these 9 countries in all these fields. And right now, we have started conducting the quiz among the school students, school children from class 9th to 12th standard. That's a quiz contest started on 22nd of February, and it will continue till 20th of March. Basically, the quiz is related to the climate science. And on 23rd of March, on the WMO Day this year, we'll announce the results of the meritorious students. All the participating students, of course, will get the participation certificate. But the first top three students from each of the 9 countries will get some special awards, including interaction with some eminent scientists, a citation, and also the ebook. So the quiz contest is going on right now among the school children. Well, as I said, we started the publishing newsletter. This is one of the newsletters of SAMA, quarterly newsletter. Then we have now in this period, we have developed the website of SAMA. We have a Facebook page of SAMA. We have a Twitter account of SAMA, and we are also on the YouTube channel. This program is being live streamed on the YouTube channel of SAMA. So highlights of the future plans are registration of SAMA. In fact, we have already filed the papers for registering the SAMA officially. And then, of course, opening the bank accounts for many transactions, financial transactions, exploring funding resources for conducting regional programs, encouraging the member countries to establish country-wide chapters of SAMA, monthly webinars on the topics of regional importance to be continued, recently constituted scientific committees for satellite meteorology, NWP, radar meteorology, air pollution, and climate change will develop capacity building programs for research and development of the region, conducting need-based training workshops for the member countries to improve their meteorological and hydrological services, explore the possibility of partnership with more regional agencies in addition to EC mode and RIMES, develop linkage of SAMA with other international agencies in this field such as IFMS, EMS, WMO, etc. Develop regional research projects, mentorship to young researchers and students by senior scientists, work with national meteorological and hydrological services, regional associations, and civil society in promoting application of meteorology for public safety and social benefit. Societal applications, climate change, agriculture, aviation, energy sector, and engage private sector in promoting application of new technologies in instrumentations and software in meteorology. So these are some of our future plans. In fact, this has already been discussed before our members, the esteemed members of SAMA, but I just try to present this once again because there are many new delegates that attend this webinar. So I just thought to share our activities with all the new delegates. This is just a glimpse of the advisory committee meeting that we had on 18th of September. And thank you so much for your attention. Thank you very much.
Thank you, Professor Dr. Somesh, for your class. Now I request Dr. Fatima Akhtar, University of Dhaka, Bangladesh, to introduce the eminent speakers who will be talking on the works of the Nobel laureates.
Now it is the time to introduce our today's speakers. Honorable Professor Tetsujo Yasunari is the advisor RI8N KCCAC Japan, will talk on the works of the Nobel laureates, Professor Chiyokoro Manabe. And Professor Krishna Achyuta Rao, head of CS IIT Delhi, will talk on the works of the Nobel laureate, Professor Klaus Hasselman. Professor Tetsujo Yasunari is chair of the Future Earth Japan National Committee under the Science Council of Japan. His field of specialization are meteorology, climate dynamics, and global environmental change, including human impacts on the Earth climate system. Professor Yasunari received his PhD from Kyoto University in 1980. With his dynamical career, he was awarded by multidimensional organizations. He served as professor at University of Tsukuba and Nagoya University and is currently Professor Emeritus of these universities. He was a member of Joint Scientific Committee of the World Climate Research Program, WCRP. Professor Yasunari is a review editor of IPCC AR6 Working Group 1 and also served as a review editor of IPCC AR5 and is a contributor for IPCC FAR and SAR. Since April 2013, he has been the Director General of the Research Institute for Humanity and Nature, RIHN, in Kyoto, Japan. Professor Yasunari is a member of the International Science Committee for Future Earth. He is Fellow of Japan Geoscience Union. Our second speaker, Professor Krishna Achyuta Rao, has been with the Center for Atmospheric Science of Technology, IIT, since 2007. Before that, he worked at the Lawrence Livermore National Laboratory in California. Professor Krishna did his PhD and Master's Engineering from the Tulane University, New Orleans, Louisiana, USA. His research area has focused on using climate models to understand how Earth's climate is affected by nature, as well as anthropologic factors, and how it will impact natural and human systems. His current interests include attribution of extreme weather events, changing risk of extreme events under a warming climate and adaptation, climate change. Professor Krishna is lead author on the 6th Assessment Report Working Group 1. He serves as member of the CLIVAR Scientific Steering Group as well as on numerous national and international research advisory and review panels. Professor Krishna is a reviewer of many international and national journals like Climate Dynamics, Journal of Climate, Climate Research, Climatic Change, and so on. He is the member of American Geophysical Union AGU, life member of Ocean Society of India and Indian Meteorological Society. Thank you. That's all.
Yeah, thank you, Dr. Fatima, and also thank you, Dr. Rohini. And now I request Professor T. Yasunari to talk on the works of Nobel laureate Professor Sukuro Manabe. Professor T. Yasunari.
Yeah, thank you very much, Namaskar. I'm Yasunari. I'm very happy to join.
Yeah, Professor T. Yasunari, can you just change your webcam, then you make it up, little up.
Can you see?
Yeah, we can see you, but half head is cutting. So, yes, it's perfect.
Okay.
Yeah.
Yeah. Yes. You know, I'm very happy to join this the South Asian Meteorological Association meeting because you know the research started from the Indian monsoon and the Himalayan climate research, and you know I have been India, Nepal many times, so I know that you know I already know the many friends here in the webinar, so this is a very nice my opportunity for me to join and talk with you. By the way, today I've been asked to mention about the work of Professor Dr. Shukuro Manabe, because you know I have been working with him for a long time, particularly when I was the professor of Nagoya University. He visited our institute for many times, and for I think actually more than the nearly 10 times he joined our institute university, and we really enjoyed that they joint talks and seminars, and you know he helped very much to our project in our university. So today I'd like to briefly show from my point of view what he has done, and what including his the personality as the researcher or scientist. I want to share the kind of well, which is can you see the slides?
Yes.
Yes,
okay.
Yes, we can see. Please make it full screen.
Okay. So
yeah,
this is
perfect.
Okay. Okay. So this is a picture of Professor Suki. You know we call him Suki in many for Americans and foreigners, but we just call Manabe-san or Manabe Sensei. And the photo in the right-hand side is a photo when Manabe-san visited the Nagoya University. I think maybe several years ago. So I'd like to introduce the main works research by the Dr. Manabe. I think there's several items or issues, particularly which he's very much interested in. One is, of course, his field is the development of the global climate models, including physical processes of atmospheric rigidity transfer, cloud formation, surface hydrological processes, and atmosphere-ocean interactions. And also there are the finding of the climate responses to changes of the atmospheric, the carbon dioxide or greenhouse gases by the human activities, and also the the impact of the change of CO2 in the glaciation in the past. And third, he also has been very much interested in the role of large-scale topographies on the general circulations of climate, and also the Asian monsoon system. And then he is very much interested in the changes of hydrological cycles and the land surface processes in the climate system, also including the impact of the atmospheric CO2 increase. And also finally, he is also very much interested in the dynamics of paleoclimate, including the past glacial cycles, and the role of the ice sheet and the deep water ocean circulation, which I briefly will mention later. So first of all, we feel that the Dr. Shukro Manabe's basic philosophy on climate modeling is simplicity and balance. This is a very the important point of what he has done, because he has done a lot of the modeling works since the 1960s up to now, and but there should be a kind of the philosophy of the climate modeling, and basically I can summarize that the simplicity and the balance is an important aspect of his the modeling. There are many people are working on the climate models, climate modeling, to simulate the many aspects of the climate and the climate change. But I think maybe Manabe Sensei's the focus is all the time what he wants to know, and then what kind of the processes, physical process, should be included, and what kind of the modeling should be done. So I think the processes and also the modeling kind of the methodology should be a kind of the integrated part, and this is a very, very important point. His modeling is not necessarily a kind of the sophisticated, the high resolution modeling, but he has the shown the many aspects of the important point of the climate system. I would like to briefly overview his work from the 1960s. So this is a very famous diagram of the atmospheric, the vertical, the structure of the. So now I think many, I think most of the textbooks in the meteorology and the climate atmospheric sciences show this kind of diagram, and but I think that this paper by the Manabe and the Strickler was a first time how this kind of structure, the vertical structure, it exists from the surface, troposphere, and the stratosphere. So this is very pioneer work, but to show this kind of the simulated the profile, he conducted a very intensive the study on the radiative transfer, which originally was developed by Professor Yamamoto of Tohoku University in Japan. But anyway, this is a kind of very, very beautiful result. And it's the left-hand side is the result, the figure from the latest IPCC report last year on how the temperature the changes due to the CO2 increase. And this is and of course, as you know, in the troposphere generally temperature increase, but in the stratosphere the temperature decreased. But this aspect of the global warming was first pointed out by the Manabe and Weatherall in 1967, this diagram. So, you know, I think this is a kind of application of this, previous work in 1964. Then he put that CO2 in that the vertical model, and the one-dimensional model. And he found that if the CO2 increase, the temperature, of course, in the troposphere and the surface increase, but in the stratosphere, he found the temperature decrease. So now this is a kind of evidence of the global warming or the greenhouse effect. But this was firstly pointed out by Manabe and Weatherall already in 1967. Then, you know, he developed a general circulation model, and using that model in 1974, about already 40 years ago, there were more than 40 years ago. But please look at the schematic diagram of the model. Yeah, this is very simple, the general circulation model. The land and the ocean, it's kind of, you know, the cyclic continuity, and, you know, there's no geographical distribution, etc. But basically, this model includes the fundamental climate processes, including the hydrology, heat balance, and also the moisture transport, etc., etc. So and then using this simple GCM, he showed how the temperature, the climate changes associated with the CO2 increase. This is the famous one, Manabe and Weatherall. So this is one of the result. This is the latitude, the vertical profile of the temperature change associated with the doubling of CO2 compared to with the standard or control run. So he noticed that, you know, the large temperature increase occurred in the Arctic, in the higher latitudes, in the lower troposphere, and also, of course, the temperature in the stratosphere decreases. So and why this temperature increase in the Arctic occurs? So this is a result. No, this is as you know, in the Arctic and polar region, there's the sea ice and the snow covered in the colder season. Then, you know, there's a kind of the feedback between CO2 and also the surface albedo of the snow and ice. Our temperature increase, and then the snow or albedo decrease, and also snow depth decrease. That kind of the sort of positive feedback, you know, enhance and increase the temperature. So this is very, you know, the simple process. But I think I think that this kind of temperature distribution is also the mentioned first time in the climate community. So this is the newest IPCC report. Of course, you know, there's a very nice figure of the very large the temperature increase in particularly in the Arctic region and then higher latitudes. So this, of course, you know, this pattern is very, very rough, and but you know, qualitatively, he already pointed out this kind of features using very simple model. Then, you know, the Manabe-san focus on the effect of the topography, large-scale topography, such as the Tibetan Plateau and Himalayas, and you know, Rocky Mountains and Andes Mountains, etc., and how the atmospheric circulation changes due to this large-scale orographies. This is also I think, the first attempt of the modern community in 1974, I believe, 73. Then it is Manabe and that represents work. Then he built 3 shows with mountain result and with no mountain results. So this is the surface, near surface pattern, pressure pattern. You notice that, this is January case, winter time. With mountains, they noticed that, there's a so-called Siberian high, very strong Siberian high to the north of the Tibetan plateau, and also the this pressure ridge along the Rocky Mountains. But if we remove the mountains, we cannot see the clear such kind of the pressure system in the northern winter. This is upper and also this is the 500 hectopascal. Again, we noticed the very realistic trough ridge system associated with mountain topography appears. Ridge, trough, ridge, and trough appears here. But if we remove the mountains, the circulation is very kind of they are circular, and no effect of the mountains. And also this is the longitude height section of the height. This is their potential height. You notice that with mountains, they can simulate well with the observation, but if without mountains, this is a result without mountain. This is quite different from the observation. So there's these results show the strong effect of the mountains on the stationary waves, particularly in the northern winter. And also this is the computation of the cyclone, the tracks, if with mountain model without mountain. So with mountain, we could see the kind of storm tracks over the North Pacific and North Atlantic very realistically with the mountain. But if we remove the mountains, the cyclone tracks are more poleward, and there's no structure of the in the whole longitude to east-west the direction. And also the role of mountains in the South Asian monsoon circulation. This is a famous paper by Han and Shukma Manabe. So again, now this is computed the near surface circulation. This is streamline. This is the southwestern monsoon flow, well simulated. This is observed one. And again, in this study, he also compared with mountain case and without mountain case. In this case, of course, this Tibetan plateau is a very important holography. So if we put the mountain Tibetan plateau, the so-called monsoon trough is well simulated, very close to the in the real system. But if we remove the mountains, this the low pressure system move far forward, and there's no kind of monsoon trough anymore. So this is the vertical, the latitude section of the zonal wind. Again, there's if we put the mountains, yes, I think this is a kind of easterly, tropical easterly jet stream appears. But if we have no mountains, the mid-latitude westerlies far move southward, and no clear easterly jet. So from this study, we noticed that the Himalayan mountains, Tibetan plateau is really important for the Asian monsoon system. And this is also the kind of meridional circulation along the Indian sectors. This is with mountains. This is without mountains. So the only with mountains we can have the vertical motion with precision near the foothill of the Himalayas and also the Indian subcontinent. But without mountains, this so-called ITCZ is located only very close to the equator, around 10 degrees north, etc. So I think this is also very nice, the result of the impact of the mountains on the Asian summer monsoon. Then, as I mentioned, Manabe-san is very much also interested in the hydrological processes or the hydrological cycles of the climate system, including the impact of the human activity. I think this is one of the first case by Delaware and Manabe on the influence of the potential evaporation on the variability of the simulated soil wetness of the climate. And he concluded that if soil moisture is interactive with the atmosphere, then the interactive soil moisture substantially increases the variance of the surface air temperature for regions with large potential evaporation values. And particularly this kind of the interaction occurs primarily at low latitudes, at all year and at middle latitudes, particularly during the summer months. And this is a kind of strong area of the stronger interaction between the atmosphere and the soil wetness. The India is here. You can notice that Indian monsoon region is one of the highest interactive the region of this hydrological processes. So I think this is one of the important the result of hydrology in his work. And then this is another in this case he attempted he made attempt to see the impact of the increase of the CO2 on the soil wetness, and he noticed that the overall drying of soil surface occurs on the northern summer high and the mid latitudes due to early occurrences at summer case. They are due to the earlier snow melt and the less cloud cover induced by higher surface temperature. So this is kind of positive the feedbacks between the kind of snow melt, snow cloud cover, and soil moisture. So generally in the northern summer over the continent, the soil wetness or soil becomes drier. I think in the recent IPCC report also showed a very similar, basically similar one. And the Manabe's group, revisited this processes in this case by using a more sophisticated model. There's in this case a coupled atmosphere, ocean, land model. And then, but I think the conclusion is very similar with the previous one. In the middle and high latitude in the northern hemisphere, soil moisture tends to decrease in summer, whereas it increases in winter. So, however, in many semi-arid regions in the subtropical and mid latitude, soil moisture is reduced during the most of the year. I think basically this result is similar to the IPCC report. And also this is they focus on the river water charge, the runoff. I just show you, for example, the Ganges River in India and Bangladesh. The associated with the CO2 increase, the runoff increase overall very considerably. And also this is the right-hand side is their precipitation. Precipitation basically changes in summer, the increase, but in some area, particularly, there's a drying occurs in the subtropical region very clear. So this is basically the same as the IPCC report. So finally, I'd like to briefly mention about the impact of the so-called the thermal hairline circulation or the deep water circulation in the North Atlantic, which is very crucial for the ice age climate also, and also the glacial and the interglacial cycle. So in this case, this is Manabe and Stauffer. They used their full couple model with including their deep ocean circulation. So not only the surface, but also the whole ocean area up to the 500 meters, several thousand meters depth included in this model. And they found a very interesting feature of so-called stable the equilibrium. This is this is 1988. It's a very famous paper. This is also the I believe the first attempt of this kind of feature in the climate community. Well, I think this is since time is short, just I show you there's a two stable state. One is this is the latitude and the vertical section of the ocean circulation, in this case, a stream function of the in the ocean. So this is the north and this is south Atlantic, the section. So there's one state is a very active deep water circulation as it is now present. But in some case, in some different initial condition, there is a kind of this kind of no deep water circulation appears. And also the if there is a active deep water circulation, the SST over the North Atlantic is relatively warm. But if there's no deep water circulation, relatively cold. So this kind of difference appears. It happened to appear, they say. Then again, in the more recently, it's at 2003, but they also try to the focus on this kind of equilibrium state issues by in this case by changing the atmosphere CO2 concentration. And you notice that this is a kind of temporal variation of the CO2 change. And then what happened in the circulation. So again, they noticed that the two kind of pattern. This is active, the thermohaline circulation. This is the north and this is south along the North Atlantic Ocean. Very strong thermohaline circulation, deep water circulation appears for the all case except the halved current CO2 case, very cold case. In the case, it doesn't show the kind of this circulation. So I think this is maybe related to the glacial period stage. But even in the current condition, there's another state. Even in the control run, the CO2 is as it is now. And there's one state of weak thermohaline circulation. So, and this is the CO2 change. So I think this is a very interesting point where maybe some kind of the water vapor and the salinity conditions two kind of stable state appears. But in the very small CO2 case, like the glacial period, so they found only one stable state. I have, sorry, I have I have no time to mention the detail. But anyway, there's so many research out of from the Manabe-san's result. So, but this is my kind of the impression, what I have learned from the Manabe-san's work. So one is, I have not been doing research to understand and solve the global warming. So an insatiable curiosity about the Earth's climate and its changes, or the Earth system itself, where we are living, is a source of my research. So all the time, the Manabe-san's idea is a sort of a curiosity driven, rather than kind of a solution oriented the idea. But anyway, this is a very important point of his research. So all the time he mentioned the word curiosity driven. Curiosity is really important for science, which is true, I believe. And also about the climate or climate model. So no climate model is perfect, and it is important to combine the necessary physical processes with the time and spatial scales appropriate to the research objectives or issues or interests in a consistent manner. So that is the important point. So this the simplicity and the meaning of the simplicity balance is, I think, this one. So I think just already 1 or 2 years ago, he finally published one book. It's a kind of the integration of the whole work and with Dr. Broccoli. The title is Beyond Global Warming. So I think if you have interest, please read this book. It's published from the Princeton University Press. So I think I had better stop here. Yes. Thank you very much for your attention.
Yeah, thank you, Professor Yasunari. Now I request Dr. Sogoto Paira from BIT Misra, India, to moderate the question and answer session. And also, Dr. Sogoto, if you want any participants to talk or bring into video, you just tell us, our team will help you.
Okay, thank you, sir. So I start with a few small questions by a few of the audience. And the first question by Prachi. So she wants to ask, these climate changes only due to global warming? Cannot there be any other reasons or not?
Is this a question to me or no?
Yeah. The question's to me.
Yes,
I think some students have asked.
Well, I think there's the Manabe is of course he's thinking that the CO2 increase is one of the very important the cause of the global warming, particularly in the recent century or so. So that's why he introduced the 19th century's work by Arrhenius and others. And his curiosity is it true or no? That's the same question. So that's why he started the kind of the simulation by putting the increase of CO2 and how the climate changes. So this is his the original motivation. So then he noticed that it's also the temperature near surface and the troposphere is increasing, and the polar region increasing, and this is just now the observational evidences. So, but I think I'm not sure whether this is a reply to your question or no. Of course, that he is also very much interested in the, the paleoclimate, and he of course know the, for example, the warmer climate in the, for example, in the Cretaceous or in the about 50 million years ago, and he also has done the similar work by using the atmosphere ocean coupled model, and he noticed the kind of the the warm climate at that time by putting the large CO2. But at that time, the CO2 increase is not by human beings, but by the more tectonic cause he mentioned.
Thank you, sir. It's actually a wonderful talk, but there are few questions which are striking in the basic type of, but still I want to ask that is there any details work with the interactive soil moisture or not? So
I think so 20-30 minutes is not enough to introduce the how the Manabe-san's work. So please many his papers. He has published, I think, several hundred papers already, and some summarized in the book published 2 years ago. So I think the one good thing is to read his book. Then there's a kind of many references already, of course.
So there are few, I think those questions are more welcome, at least in today's context. So a little bit philosophical, but it's very important. Is there any hope to going back to normal from what we see in climate change scenarios, since the system is more natural than artificial now? More artificial than natural now, I hope. So the question is that can we go back to the normal stage at because climate change already took place. So can you return back? Will it be possible to return back?
Oh, please ask the Manabe-san. But anyway, okay. I am also I was having involved in the IPCC. So I think I need to mention a little bit because now the CO2 is increasing. This is I think real. And now there are the many countries, all the countries are now they're trying to reduce their CO2 emissions to zero, hopefully 2050. But even though this zero emission is realized, I think now the temperature is still there, still going for a while because because of the ocean. The ocean already have a huge the carbon dioxide inside, and so that should be gradually released even after the zero emission. So that's why they are not only the climate mitigation but climate adaptation issues crucial. So I believe it is in
thank you. Mohan, so should we have time to go for more questions?
Yeah, I think we can take one more question. Raju Atada want to ask question to Professor Yasunari.
Yeah, with the interaction mode.
Yeah. Dr. Murli. Yeah, hello, Dr. Raju Atada. Yeah.
Hi, Professor Ranjit. Yeah. Thank you. Can I ask the direct question to Professor?
Yes, please go ahead, please.
Okay. Thank you, Professor Yasunari for the astonishing talk. So I just wanted to ask one question about his model, Manabe's model, which is basically explained all the climate science, most of the climate science problems. Okay, so in order to determine vertical thermal structure, the great thing he did is that he fixed relative humidity than absolute humidity. So then he got accurate absolute profile and temperature profile of the altitude.
Mm-hmm.
Can you elaborate, like, what is, I mean, like people, I mean, this, we know that it is the smartest step to get the realistic vertical thermal structure for the through the radiative convective model. Could you please elaborate it? What will happen if we fix the relative humidity than absolute humidity?
Oh, that is a very, very crucial and important question. And also, you know, in the Manabe's paper, they discussed about one. I'm not sure why, you know, this relative humidities. I think I think maybe think about, you know, the climate system. What what is happening in the real climate system, which is more kind of, you know, they are similar. So okay, I need to be revisit his paper, but I think maybe, you know, yeah, he basically referred to the the atmosphere state. So so it's very difficult to say that the reason why he chose. So I think this is but I think a very good question, and I think maybe maybe this is a kind of issue for future. But anyway, the result show that, you know, yeah, it's very similar to the real temperature profile. So there should be some kind of the hidden processes or no, I'm not sure.
Thank you, Professor Yasunari, and we will move to the next session, next speaker. So thank you, Dr. Sogoto, also. Thank you. Yeah, thank you. So now I request Professor Krishna Achyuta Rao to talk on the work of Nobel laureate Professor Prof. Hasselman. Professor Krishna Achyuta Rao.
Good afternoon. Yes. Thank you for inviting me to speak on Professor Klaus Hasselman's work. I'm going to share my screen. Please let me know if it is visible and you can see my presentation.
Yeah, we can see. You can make it full screen.
Okay. Right. So
can you yeah. Okay. Thank you.
So I'm going to touch upon the work of Professor Klaus Hasselman. Professor Hasselman started as a physicist and worked in oceanography. He spent some years at the Scripps Institution of Oceanography in San Diego for a few years, and then moved back to Germany, where he had his earlier education. And he was the founding director of the Max Planck Institute of Meteorology, which is one of the premier centers for climate and meteorology in the world. So he was there he was a director from 1975 to 1999, and he has been an emeritus at Max Planck since then. Now, his interests are wide-ranging. In fact, since he became emeritus, he had been working on some of the fundamental physics questions of the unified field theory. But what I'll do today is sort of give an overview of two seminal papers of his, which were fundamental to understanding the field or which were fundamental in establishing the field of detection and attribution of climate change. So this area is essentially the problem of how do we know that human beings are causing climate change and not natural causes that there may be. So the first paper that is from TELUS in 1976. This simple sounding title, Stochastic Climate Models, where he basically lays out the difference between weather and climate. Now, weather, as we know, is something that's rapidly changing. But from weather to climate, as we understand how changes are propagated, this was a very, very crucial paper. So, the fundamental idea that he has proposed in this paper is very simple. The short-term weather variability leads to long-term climate variability. So this is developed through a series of statistical arguments, and his primary conclusion is that the timescales of the weather system and the climate system are well separated. So we will come to what it means by well separated. As a consequence of this timescale separation, the response of the climate system to random forcing by weather can be described as a random walk or diffusion process. For those of you who understand statistically, this is a first order Markov process. So what does this mean? So he had this figure. This is a figure from a later paper by a companion paper, part 2 of this, with Frankengool and Hasselman. Essentially, this is looking at the North Atlantic, where surface pressure varies almost across all frequencies. The variation, the power is the same. Whereas if you look at the SST in the North Pacific, it's got a peak at low frequencies, right? So a similar kind of thing, if you might say, atmospheric forcing is a white noise spectrum, where at all frequencies you have uniform sort of power. But if you look at the SST, then most of the power is concentrated in the low frequencies. And this is an actual plot of measured 500 millibar temperatures, which is kind of got variations of equal power across all frequencies. Whereas if you look at the SST, the high frequency component is completely damped, and it's the low frequency that is. So this in a sense means that the ocean is integrating the variations in weather to create the climate. And you can, and this is up to decades and centuries. This is the kind of thing. And then when you go into millennial timescales, the SST variations and the ocean variations influence what happens to ice sheets and things like that. So this finding then basically, it also has implications for what happens to changes in the stochastic forcing. If you change the amplitudes of forcings from the atmosphere, this is going to end up making variations in climate, and that's the change that we notice. And these rely to a large extent on internal feedback mechanisms. If it wasn't for feedback mechanisms, these stochastic variations can lead to runaway change in climate states, etc. So, and this also has implications for predictability. So this essentially, the fact that the ocean integrates these variations means that we can actually use that to predict future climate and to some extent even the weather, because the memory, if you will, is staying in the ocean. So this is the first of his seminal papers where he actually lays out the separation of timescales between weather and climate and how that can be useful. The second paper, which was actually conference proceedings, and it is obscure. It's not in a journal, but it is one of the most highly cited papers in climate science, is on the signal to noise problem in atmospheric response studies. So this is where the whole field of climate change detection and attribution was introduced. So essentially what happens when climate changes is that there is a measured change, but is that measured change larger than the variations that would normally occur when you had no changes in forcings? Because of the stochastic nature of climate is always going to vary, and therefore are the changes that we are experiencing larger than what would have occurred naturally. So this is the first step of understanding whether there is an actual change, is what we refer to as detection. And then the attribution part comes to whether we can say with some degree of confidence what caused that change. So it could be natural factors or anthropogenic factors, as the case may be. But let's see what this paper did. So essentially, it is necessary to regard the signal and noise fields as multidimensional vector quantities, and the significance analysis should be carried out with respect to this multivariate statistical field rather than terms of individual grid point statistic. So you cannot look at changes occurring at individual locations to make sense of the larger climate change, because the noise at individual grid points can become larger. So just to quote from his paper, basically what it would be, what he proposed is to use numerical experiments from general circulation models, or GCMs, rather than looking at individual grid points. What he suggested was to do some kind of a filtering. Without filtering, either in space or in time, or more commonly in both space and time, you will end up with too many degrees of freedom, 10 to the power 3 to 10 to the power 4, and that is too many degrees of freedom to be able to analyze the data properly. So by filtering, either averaging in time or in space, you are actually reducing the number of degrees of freedom to a more manageable range. And that will allow for a more robust way of separating the signal from the noise. So this filtering is clearly something that he proposed, a pattern filtering. And this is what he suggested, is that if you have some prior knowledge of what pattern you expect that change to be, so in a sense, he said, if you have a guess of what the pattern of change is going to be, then that will allow you to look for that pattern in your actual observation. So rather than searching for a needle in a haystack, right, in a sense of multidimensional climate variability, where you have many variables, many degrees of freedom, basically his contribution was to say, okay, if there is a model simulated change which is based on physical understanding, whether it's a response to greenhouse gas or to something else, then look for that pattern in your observations. So so in a sense, it was it was flipping the problem and saying, here's the problem, here's the pattern of change you expect. Is that pattern visible in the observations? So that's the basic of this. But but the pattern that one gets from GCM simulations, these patterns could also be varying in the same way as in the real climate due to other causes, natural causes. So his solution was to actually use what is called an optimal fingerprint. So if you just take the pattern of change that is guessed, that would be the fingerprint. But if you look at where that pattern is most distinct from natural variations, that would be what is called an optimal fingerprint. So in a sense, this is like taking an EOF and rotating the EOF to a direction that is orthogonal, basically where it is most distinct from what you would consider noise. So just to give you an example, before I go to give an example, so this thought of what is the pattern of change one expects is therefore an important thing to have. And it has to be said that at the time, 1979, when he wrote this paper, general circulation models, coupled general circulation models were still conceptual. Manabe and his colleagues at GFTL and the people at Max Planck Institute in Hamburg were all working on developing this coupled model. So there weren't yet these simulations that would be able to give us the pattern of the expected structure. Although there were, as you heard from Professor Yasunari, there were already simple models, one-dimensional model calculations that showed kind of what you might expect from Manabe-san's work. So what are the kinds of model simulations that one needs? Because one is to have a sense of what is the climate noise. When we say noise in this context, it is all these random internal fluctuations that happen to climate when nothing is changed. When you don't change anything, whether the sun's radiative output or any of the greenhouse gases or other things that change climate, if nothing changed, the Earth's climate will still be highly variable. So these variations that occur due to the nonlinearity of the climate system is what we call noise. So these noise estimates are produced using long control runs of what we, in today's jargon, call pre-industrial climate, basically climate before human influence became a factor. So these long control runs did not exist. And then there were also no simulations that said, if you only had greenhouse gases, this is the pattern of change you can expect, or if you had aerosols, this is the pattern of change. These days, of course, today, under CMIP 6, we have all of these kinds of numerical experiments, long control runs, and these what are individual forcings that are applied to climate models. All of these exist. But back then, when he proposed this methodology, none of this was available. So in a sense, this in itself was leading to the kinds of experiments that people today perform, is based on the kinds of things that Professor Hasselman did. So I'm just going to give you a sense for what these different experiments might show and what does it mean to optimize a fingerprint. Okay, so this is from a recent paper written by one of my students. So this is the EOF pattern of change in the historical last about 100-year period of surface air temperature over India. So if you had all the forcings, both natural and anthropogenic, you have a pattern of change that looks like this. Greenhouse gases alone indicate a pattern of change that looks very similar to what the combined forcing is. Now, natural forcings and anthropogenic aerosols have a cooling effect, and that's why they have a pattern of change that looks like this. So greenhouse gases and anthropogenic aerosols, when you combine them, the kind of temperature change that you expect looks like this, and this is the anthropogenic. So these are patterns. Some of them look very similar. The anthropogenic and the greenhouse gas patterns are very similar to when you have all the forcings there. But you can actually do, if you rotate or optimize these fingerprints, you can optimize them through various techniques depending on how many modes of empirical orthogonal functions you want to take for in the noise. So you can see that you can produce this patterns that you end up with look very different from what the actual change pattern might be. Okay, so these look exactly like what the trends in temperature would have been, but these optimized fingerprints don't look like that. But by rotating these EOFs, we are able to get to a more to a pattern that is unlike what the natural noise pattern looks like. So based on this, based on his work and in the first assessment report of the IPCC in 1990, what they wrote is that the detection problem can be conveniently described in terms of the concepts of signal and noise. Here, the signal is the predicted time-dependent climate response to the enhanced greenhouse effect. The noise is any climatic variation that is not due to the enhanced greenhouse, so something that occurs naturally. Detection requires that the observed signal is large relative to the noise. Okay, so, and in addition, in order to be able to attribute the detected signal to the enhanced greenhouse effect, it should be one that is specific to this particular cause. It cannot be that, you know, you can have the same pattern of change from multiple things. These have to be distinct patterns. And I'll give you a couple of examples of this. So this was in 1990 when, you know, the papers of Manabe and Hasselman and everything was assessed. And what we knew at that point was that this could be done, but it hadn't yet been done. On the basis of this same IPCC report concluded, we might conclude that detection with high confidence is unlikely to occur before the year 2000. When they said that the signal will be large enough that it will have become bigger than the noise. However, long before the year 2000, in fact, 3-4 years after the IPCC report came out, there were a series of papers by Ben Santer and others working with Klaus Hasselman. Ben Santer was a colleague of mine. He did his postdoc under Klaus Hasselman. Another paper, another postdoc of Klaus Hasselman's, Gabi Hegel. She produced this paper which looked at the surface air temperature. And these Santer's paper looked at how you can use the fingerprint method or the guess pattern, as Hasselman's terminology went. So these three papers by 1996 were out there. And in fact, in 1995 itself, when these papers were published, the IPCC second assessment report suggested that the balance of evidence suggests a discernible human influence on global climate. So let's see what, when Ben Santer and his colleagues wrote about the vertical structure, this 96 Nature paper, Search for Human Influence on the Thermal Structure of the Atmosphere, let's see what that was. So this is a series of experiments that were performed with a model called the parallel climate model. This was run at the National Center for Atmospheric Research. So what this model had, they had done with this model, this is Warren Washington and Jerry Meal were responsible for this model. They had these experiments where there were these individual forcings. So this is a simulation showing the change in temperature at various pressure levels between 1958 and 1999, where the model included only changes in greenhouse gas concentrations. And you can see here that this is the pattern that Professor Yasunari showed, where the troposphere is warming and the stratosphere is cooling. So this is going back to Manabe-san's work, where the tropospheric heating and stratospheric cooling is clearly visible, even in a much more sophisticated model. This was run in the 1990s. Sulfate aerosols, if you have a simulation of the same model with only sulfate aerosols, then what the pattern of change indicated is that there is a cooling of almost the entire stratosphere troposphere column, with a larger cooling in the troposphere, some warming because of associated effects with ozone that occur in the polar stratosphere. If you look at stratospheric and tropospheric ozone changes, right? So this is increased ozone in the troposphere and stratospheric ozone loss. There's a cooling in the polar stratospheres because ozone has been destroyed, and tropospheric ozone increases lead to a warming of the troposphere. If you look at volcanic aerosols, whenever you have a volcanic eruption, it ends up warming the stratosphere but cooling the troposphere. And solar irradiance changes. This is again going back to one of Suki Manabe's original papers, where he showed that when you change CO2 concentrations, you get this distinct warming troposphere, cooling stratosphere pattern. But when he did that using the same model, when he changed the solar irradiance, the entire troposphere stratosphere column either uniformly warms when you increase solar irradiance or uniformly cools when you decrease solar irradiance. Okay, so you don't have this troposphere stratosphere difference in this response to solar irradiance changes. So if you look at each of these patterns, they're quite distinct in how changing greenhouse gases or sulfate aerosols or solar irradiance affects this entire stratosphere troposphere column. And when you combine all of these forcings, which is actually what happens in the real world, you get an overall change of the stratosphere troposphere column that looks like this. So this, you can see, has features of all of these different individual forces, right? So if you were to take one of these patterns and see how that pattern is being seen in the observations as time goes on, in other words, whether this pattern is becoming more and more obvious with time, then you are able to estimate the detection. So here again, similar set of experiments. Here is what this one doesn't go as high into the stratosphere, but you can still make out this is the troposphere and this is the polar stratosphere. And you can see that there is a cooling in the upper levels. You can see this from anthropogenic forcings. Natural forcings produce a different pattern. If you just look at volcanic forcings, natural includes both volcanic and solar forcings. So if you look at each of these, and this is solar, right? So you can see that over the period from the late 1980s to about 2015, these are the trends. And these two panels here are the measured or observed trends using the microwave sounding unit and the AMSU, the Advanced Microwave Sounding Unit, the two different products, because the data from the satellites can be processed in different ways. And this is from remote sensing systems, and this is from the University of Alabama at Huntsville. So these two look different in some ways, but you can see that there are some features from each of these that are present here. Not just anthropogenic, but there are some signatures of volcanic eruptions also. And this is what that signal ends up being. If you take each of these, the anthropogenic pattern, how it shows up over time, you can see that there is a dip in the strength of the signal here. And that is because Pinatubo eruption happened in 1991. And because of that, the loading of this pattern decreased. And there is no, we haven't plotted the analogous volcanic, and the volcanic pattern shows an increase in the signal strength. Now, when you look at changes in this kind of pattern, it can happen due to natural causes also, except it won't be sustained over long periods of time. If you take 5-10 years, you can get these kinds of the same kind of warming patterns when there's a large El Nino, etc., etc. You can get this kind of pattern, but it doesn't show up in the loading. So this is noise. So when you take the ratio of the signal and noise, you end up with the signal to noise ratio, and you can see that it is growing with time. And this growing with time, you can say, is well above the 1% significance trend. In fact, further work has shown that this is above 5 sigma threshold strength, and therefore this is a robust detection and attribution. And this is all based on, so this has led to the latest IPCC report from last year to conclude it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Human fingerprints are telling us, have been found in many parts of the physical climate system, as well as in the impacts that they produce, as today's working group 2 of the IPCC, which is being released, is going to show. And so I'm going to leave you with 2 papers that I have co-authored with my students, and this is especially over the Indian region, and there are treatments of how surface air temperature over the Indian region changes, different approaches both based on Professor Hasselman's work. And with that, I'll end, and thanks. And I'm happy to take any questions.
Yeah, thank you. I request Dr. Mohan Kumar Das to moderate the question and answer session. And also, it is my pleasure to wish Dr. Mohan happy birthday. And so Dr. Mohan.
Thank you very much. Thank you. So it is really a great lecture from Professor Achyut Rao. Sir, we have received a very good number of questions from different participants. I would like to share some of them for your kind answer. Some people ask, especially Eliza Shubedi, what does what would happen if ocean acidification remove?
Ocean acidification?
Removing of ocean acidification.
I don't know of any way in which you can remove the acidification of the ocean. If you keep taking CO2 out of the atmosphere and putting it underground through some magical process, then some of the ocean carbon dioxide, dissolved carbon dioxide, will outgas, and hopefully that can be one way in which the acidification can be removed. But I think this is a huge process, and it's not something that can be easily done. Hopefully, we will reach a stage where we can remove CO2 from atmosphere and have this outgassing from the ocean to take care of acidity.
Okay. We also received some questions from the Pushti Sharma. She wants to know if the discharge of all the greenhouse gases is stopped, is it possible that the ozone layer will recover?
The question has actually confused greenhouse gases with ozone layer. The ozone layer, the destruction of ozone that happens is not due to the greenhouse effect. It is due to the chemical reactions that are happening in the stratosphere because of certain man-made chemicals that are going up there. So while those chemicals also happen to be greenhouse gases, it is not due to the greenhouse effect per se. So once we stop releasing those harmful chemicals into the atmosphere, the ozone layer should recover. In fact, there is, since the Montreal Protocol in the mid-1990s, the production of many of these chlorofluorocarbons and ozone destructing chemicals has come down, and the ozone layer is showing signs of recovery. So it is not directly connected to the greenhouse effect, but it is being solved.
Okay, sir, there is two questions. Maybe there is some slide. What is the mean by October heat, and what is the time scale separation?
I'm sorry, I didn't get the first part
sir,
of it.
First one is the what is exactly mean by October heat? October. There is some heat. Yeah.
October heat.
Yeah. Someone asked regarding this, and another is the what is time scale separation?
Right. So I'm sorry, I couldn't figure out what the first part of the question means.
Okay, sir.
But I will answer the time scale separation. So when we talk of climate and climate change, we are essentially talking of longer time periods. Okay, not the high frequency variations that we see in weather, where weather variations occur on timescales of minutes and hours and days. Whereas climate, as we look at it, is on the longer time scales. And the reason for looking at that longer time scale is when we look for changes in climate at the longer time scales, it is an integration of all the changes in the weather over that period of time. So that takes the high frequency changes, which are occurring at very short time scales, to what it becomes in the long term. So that the short time frame and the long time frame is what we mean by a separation of time scales here.
Yeah, thank you, Professor Krishna Achyuta Rao, and also Thank you, Dr. Mohan Kumar Das, to moderate the question and answer session. So we will move to the next agenda.
Thank you.
Thank you. So I would like to invite Dr. R. Krishnan, Director in charge IITM Pune, to deliver the concluding remarks.
Yeah. Thank you very much, Dr. Ranjit Thapa. First of all, I would like to thank Professor Ajit Tyagi, who is the chairman of SAMA, and Professor Someshwar Das, the convener SAMA, for giving me this opportunity. And today's two excellent talks by Professor Yasunari Sensei and Professor Krishna Chutarao on the outstanding scientific contributions of Professor Sukiro Manabe and Professor Klaus Hasselman. I really enjoyed both the presentations and excellent talks. And also I would like to thank all the eminent panelists today and also Professor Narayan Rao, Pro VC SRM University, Dr. Mandira Sreshta, Dr. Rohini Bavar, and also Dr. Professor Madan Sreshta, and all the eminent people who have gathered today. I particularly liked Professor Yasunari Sensei because I had an opportunity to work at the Frontier Research System for Global Change during 1998 to 2000 in Professor Suki Manabe's group, in the global warming group, which was in Hamamatsucho in Tokyo. But actually, I worked in Tsukuba. I was staying in Tsukuba and have visited the Professor Yasunari Sensei's Department of Geoscience in Tsukuba University, and very close. And I was staying very close to his house, actually, in Azuma. I remember those good olden days. And my interactions with Professor Manabe is unbelievable, amazing. And he's according to me, a scientist par excellence. And as Professor Yasunari really mentioned, he pioneered physical modeling of the Earth's climate and the global climate change research. And he made several landmark contributions, all first time. He was the first in everything on a whole range of scientific topics, which many Professor Yasunari Sensei has nicely covered. And his emphasis was on to understand the scientific problem in a very simple way. And also he was very inspirational. So when you talk to him, he was full of positive energy, full of enthusiasm, very kind and helpful. And it's amazing that we have had an opportunity to interact with such great legends. And that itself is a big blessing. And thank you very much, Sama, for giving this opportunity. Today was an excellent program. If you don't mind, I would like to share one slide with showing with Professor Manabe Sensei at Frontier. Just one slide.
Yeah, please.
Share. So is this visible?
Yes, perfect.
Yeah. So this was during 2000. This was during the Frontier Award ceremony. And I was returning back to India after 2 years. This is Professor Matsuno, another great legend. And these are Professor Manabe here, Professor Matsuno, and our Indian colleagues, Dr. Bera and Dr. Saji. And then this was during the farewell at Frontier Research System for Global Change. I worked with Dr. Masato Sugi, who was actually a program director. And this is a picture with Manabe Sensei and Sugi-san. And these are all our meetings there. And actually, we had a wonderful time. And this was during the farewell with my family. And later in 2004, I visited Professor Manabe Sensei in Princeton. And he was so kind, he took me to his home. And this was a picture with his Rosby medal. And this is Mrs. Manabe-san. And it's an amazing thing. I thought I will just share with you. It's a great person. And I really enjoyed. I'm very thankful. I cannot forget those golden days. And Many thanks to Sama for this opportunity. Thank you very much.
Yeah, thank you, Dr. R. Krishnan.
Yeah.
And also to participants, actually, we want to announce that the merit list of the student in climate science quiz will be announced on 23rd March on WMO Day. So because the competition is extended till 20th March 2022. This is for information. So now I'm moving to the next agenda. So I would like to invite Dr. Mandira Srestha, ICIMOD, Kathmandu, Nepal, to deliver vote of thanks.
Can we have a photo session before that?
Yeah, you want after or before?
Before. Some people might leave quickly.
Okay,
Before is
okay.
better.
Yeah, so it is better than let's all on our video. So please, every panelist on your video. So I request all the panelists to on video. Yeah, Dr. Professor Ajit Tyagi. Professor Ajit Tyagi. Hello, Professor Ajit Tyagi is there? Hello, Professor Ajit Tyagi. Yeah, can we go ahead or? Lakshmi Kumar?
Professor Tyagi, he was busy on the call. So we'll switch on the video just now.
Okay. So who is Narsim Muradi? Mr. Narsim Muradi?
Yeah. Hello, sir. Just a minute for 1 minute or 2 minutes.
So can we take the picture, Professor Somes?
Yeah, it is done.
You have to unmute.
Yeah, it has done. So I'll share screen.
Yeah, I think we can go ahead. Yeah,
yeah, it has done.
Yeah.
Okay. Thank you very much. Thank you. Okay, so now we will move into the final things. So I request, already I have requested Dr. Mandira to deliver vote of thanks. Yeah.
Well, thank you very much, and a very good afternoon to all of you. It is indeed my privilege really to be, given this opportunity to say the vote of thanks, particularly on this, occasion where we're talking about, the National Science Day celebration with this particular webinar, very important webinar. So I'd like to thank Sama for providing me this opportunity. Now, I think the whole this webinar has been extremely interesting and informative. And on behalf of Sama, as well as all the organizing team here present, that would include Vigyan Parasar, as well as Vidyarthi Vigyan Sanstha and SRM University, and also on my behalf, I'd like to thank a number of people here, particularly I'd like to start with the keynote speakers that we had today. Professor Tetsuo Yasunari Sensei, advisor at the RIHN. I think he had an excellent talk in terms of sharing with us some of the work that of the Nobel laureate Professor Manabe, and I think that has been really inspiring for all of us, particularly when I was listening to him, the talk in terms of the role of the mountains in the Himalayan region, particularly on the monsoon circulation systems, is extremely important and continues to be still a challenge actually to all of us as it's being studied more and more, and also the work that he has done in terms of the hydrological responses and some of the preliminary estimates that he has come up with in terms of the difference in the Ganges basin that was shared by Professor Yasunari was quite informative and very interesting for me too, and I'm sure for all of us here. So thank you very much. And particularly when he said that, we're talking about a balance here, of simplicity and balance. I think that's very much important that we also look into it. So thank you, Yasunari Sensei, for that very interesting talk and for sharing your experiences. I'd also like to thank our second keynote speaker, Professor Krishnan Rao. He's the head of CAS, IIT Delhi, and his experiences that he shared, and also the two papers that he shared about the work of the Nobel laureate Professor Klaus Hasselman has been also very informative and interesting. It is always there's a question about saying, well, what is climate change really caused by? We also had this question during the session here today. Is it due to anthropogenic causes, or is there many other drivers? And I think the information that he shared about the learnings from the various work that the Nobel laureate has done has shed a lot of light, and it has been very interesting for the listeners here today in terms of looking at the attributions of climate change and global warming. So that has been also very interesting. And what he talked about, the optimal fingerprints, I think that's also interesting. And the work that continues even now and as it progresses further. So thank you very much, Professor Krishnan Rai, for this very interesting talk and for enlightening us with further work that has been done. I'd like to now thank definitely, a number of people here that we've heard today who's all very much responsible, not only for organizing, but also delivering this wonderful webinar today. Dr. Madan Lal Shrestha, who provided us kind of an overall about the webinar and some of the introductions and his experience also with Professor Manabe Sensei. The remarks by Professor Dr. Ajit Tyagi, the chairman of SAMA, as well as Dr. Narayan Rao, Pro Vice Chancellor of SRM University, has been informative and enlightening. The work of SAMA, indeed, yes, it has been about a year and a little more that we have been established. And thank you very much, Professor Sumeshwar Das, for enlightening us further with some of the work and also the mission and vision that we continue to have. I think it has been quite informative, as well as a really, really inspiration for all the people working in the region in terms of working further on this issue. Dr. Fatima from the University of Dhaka, I think she has nicely also introduced our speakers today, and with whom we had that privilege to listen to. So thank you, Dr. Fatima, for your role in this webinar. I'd like to thank all the moderators, all the 4 moderators. I think Dr. Ranjit Thapa, as well as Dr. Rohini, and did a very good job in terms of facilitating and moderating the sessions, and the question and answer sessions has been interesting with Dr. Swagata Pavra, as well as Dr. Mohandas. So thank you all very much. I'd like to definitely thank Dr. Krishnan, who has kind of summarized and also shared some of the photographs that he has with the experiences that he had with Professor Manabe Sensei while he was doing his research work in Japan. So myself, I have found the whole, webinar very interesting. And apart from whom I have named here during this webinar, I would like to thank all the participants who are here listening and waiting for listening to us for the last 2 hours. And would like to thank you for providing your questions and also your curiosity to learn more. I think, as was said by Sensei Yasunari, curiosity is extremely important, and I think this drives us to further learning. So thank you all for being here, and all the students as well as the participants from the National Hydrometeorological Services research organizations. Thank you for really being here and making this a big success. And behind the scene, there have been a number of people who have worked to put in this in the YouTube channels, as well as to have it live and in this Zoom call. So thank you all. And so I'd like to give a round of applause for all of you here today. And so, with that, I'd like to just thank you all. Yeah, so let's give it a round of applause.
Yeah, thank you, Dr. Mandira. So in formal way, so now it is finished, the webinar. Now, if there is any announcement, I'm hand over to Professor Someshwar Das. If there is any specific announcement, you can go ahead.
Well, already announced that the quiz contest has been extended till 20th of March because many students had the examination in the schools, and so we have extended this. And the result of the quiz contest, the meritorious students' results will be announced on the WMO day, that is on 23rd of March. This has already been announced. I think the next event of SAMA probably would be a specialized meeting on one of the scientific committees, that is on education and outreach, which will be announced soon, followed by the other committees, that is on satellite meteorology, radar meteorology, air pollution, climate change, etc. So these are some of the upcoming activities. And thank you very much, Professor Ranjit, for very nicely conducting the session, Professor Ranjit, as well as Dr. Rohini, both of you. Thank you so much for connecting.
Thank you. Thank you. So I think, yeah, thank you. Thank you.
Let us have the last word from the chairman, Professor Tyagi. Be there. Probably he is not there. So.
Yeah. Well, for entire SAMA team and our partners, SRM University, Professor Rao and Rohit, Ranjit, Thapa, Professor and Vigyan Prasad, colleagues are not today here because of Science Day celebrations going on. So in their absence also, we'd like to acknowledge their contribution, and especially our Shrestha's, both Madan and Mandira Shrestha, for the starting opening remarks and the vote of thanks. So thank you so much. And SAMA look forward for all the participants to join the SAMA family fraternity. So you are invited to become member of the SAMA and contribute for the growth of meteorology in the South Asian countries. As brought out by Professor Someshwar Das, we have got a lot of plans, but we require your support and active involvement. So we look forward, and I am sure we will be able to make a difference. Thank you. Jai Hind.
Yeah, thank you, Professor Ajit Tyagi. So we are closing then, Professor Someshwar Das.
Yes, thank you.
Thank you. Yeah, thank you. So we are closing the meeting.
Thank you. Thank you
very much. Thank you.